All right, so as we explore this video, we're going to be talking about lesson 221, which is about dilations. We had in class an activity where we played with decimals and we reminded ourselves what dilations were, which we learned in 8th grade. And we spent some time just kind of fiddling with them and playing. And today we're going to get into that quite a bit more. So again, this is lesson 221. Make sure you have that open and follow along with notes there. All right. Okay, so today we're going to be investigating a transformation called dilation, which enlarges or reduces a figure while maintaining its shape. After creating newly large polygons, you and your team will explore the relationships. You will, because you don't have a team, explore the relationships that exist among polygons that look alike but are different sizes. So as we explore the processes of dilating by hand, let's keep these questions in mind. What will the image look like? What does the image have in common with the original? So again, the image is the new figure I'm going to create. And what does it have in common with the original figure? And what is different? Be very, very specific. How is the image oriented, which means what directions is it facing? Okay, so let's go ahead and get started. So sketching a figure is called the dilation. What does a dilation have in common with the original figure? And we're going to see what we can do. So dilate the figure to make it twice as large. And from the origin to make it twice as large. So as we discovered in our, no, that's not what I want. In our activity, we can create dilations by using the center of a center, and then we need to be drawing straight lines from that center. So I'm going to go ahead and do dashed lines. I'm going to make them blue. See what we got. Let's see what happens. Which color do I have? There we go. That's the one I want. Okay, so we need to go from the origin and through each point. So these are very light lines because I don't want them to be in the way, but they need to be there because my points need to lie on those lines. So my new points will need to lie on the lines I've just drawn from the origin. And I think this one is not great. I'm going to do that one again. There we go. Okay, so one thing to keep in mind is we need to make sure everything becomes twice as large. So right now this is 4, and so our new one will have to be 8. So we need to lie on these lines and be 8 spaces apart. So I think here it's probably good. 2, 4, 6, 8. Yep, that's a great one. There's that one. Okay, and then I need to lie on these lines and be the diagonal spaces are weird, so bear with me. I'm just going to go with this triangle shape of down 2 over 1. I need that to have 4 of them. So I'm going to start with this point, down 2 over 1, down 2 over 1, down 2 over 1, down 2 over 1, and so I'm right here for my new place where D goes. See how I have twice this line here? See that line? And I have that, and then twice. So I'm doing great. That's kind of the idea of doing it by hand. It's a little different to do it by hand than to let the computer handle it for you. And so for C, between C and D, it needs to be 6, but straight across. So that's 6. Yep. Okay. And then between B, I need this 1 by 4, up 4 over 1, up 4 over 1, up 4 over 1, good. And there is my new shape. So I'm going to go ahead and erase the triangle I drew over here. And I got a nice, erase that triangle. Just kind of get it out of the way. So that's how you do it. You've got a couple of things going on here. One, these lines. Here, here, second here are not parallel to each other, but they do have a special relationship. I'm going to make them dark for just a minute. Just change their color to something darker. They're all emanating from the same point and passing through. And so if you recall, in the Desmos dilations, we were able to move that center around and the shape moved around. But the relationship did not, because of where they passed through everything else. Okay, so what are the lengths of the original image and what are the lengths of the dilated images? So as I was doing this, I was actually answering question B without realizing it. So as I was dilating, I was answering question B. The lengths of the original image, this one is 4 and this one is 3. And my new image, this one is 8 and this one is 6. Now diagonally, I didn't actually find the lengths. I used slope to help me on my diagonals, but diagonally it's a little different because I didn't find the distance. So I used slope to help me because I just went, okay, so there's 2 triangles here. So now I need to have 4 triangles, right? And there's 1 triangle here, so we'll now need to have 2 of them. And so that's not really length. So when we deal with length, if you were going to answer this question, we actually have to do the Pythagorean theorem a couple of times. So the Pythagorean theorem is 4 and 1, right? So 4 squared plus 1 squared, which is 16. So we have the square root of 16. Now this is going to be hard, square root of 17, excuse me. This is going to be hard to compare because I have the square root of 17. Now I mentioned in class to somebody recently about different ways to deal with radicals without using a calculator. And it is difficult, but one of them would be really helpful here. So now instead of 4, I have 8, and so these are both going to be times by 2. But when I square them, that's not going to be the same. I'm going to have 64 plus 4, which is 68. Well, it turns out that 68 is equal to 17 times 4. Okay, so the square root of 68 is equal to the square root of 4 times the square root of times 17, which is the square root of 4 times the square root of 17, or 2 square roots of 17. Now, I don't know how much you've done with simplest radical form. It is really something that I am supposed to show you how to do in this class. So if you've never seen that before, take it for what it's worth. If you have, great. If you've never seen it before, I'll prove it another way. We'll just take the square root of my calculator. Square root of 17 is going to be slightly bigger than 4. It is, square root of 17 is 4.123. And then the square root of 68 is, square root of 68 is 8.246. You can see how every number is doubled, and so we can verify it that way. So if the simplest radical form thing, you're like, what the heck are you doing? I apologize. I'll teach you about that more carefully later. But I just kind of went straight ahead and jumped in. Okay. Are there any questions? Well, you're not live. So, but the idea is every single one of them should be double because we made it twice as large. All our lengths should double. Okay. All right. Are there any questions? Again, you can't ask me questions. We're not actually live. So imagine you dilated it to 3 or 4 times as big. What would change the length? How would that change the length of the size in the original image? Create one of these dilations on the graph using the center. So I'm probably going to go with 3, maybe 4. We'll see. I'm going to get my dashed lines in here again. Let's use orange this time. So again, I have to have the dashed lines to help me. And one way to tell what you should do that I like to use, especially when I'm using the origin as my center, is actually, since looking at the move from the center through the point, so it was up 2 over 3. So if I go up 2 over 3, that's 1 dilation. I go up, that's 3. And this is 4. So you can kind of use that to help you because it's got to stay the same. So, but that only works when the origin is your center. Okay. And so that's 2. This is 3. This is 4. And this one would be 5. And you can tell my line's off. Okay. And then the same thing with B. 1, 2, 3, 4, 5. I might actually do them all here. This is supposed to be going directly through. Okay. And I really did a bad job with these lines. I should move them all. Especially that one. That one is terrible. Maybe I'll redraw them all. They're all really bad. All right, let's redraw them. Starting at the origin, passing through all of the points. Starting at the origin, passing through all of the points. Starting at the origin, passing through all of the points. So again, we did 2 already, so I'm going to go ahead and do 3 times as big. And when I do this, I'm connecting the 3rd point, counting the corners as the first. And this is 4 times as big. Five times as big. Kind of looks like a spider web. And 2 we already had, but I'll do it again. And what you should be able to see is kind of this telescoping situation happening, where everything's kind of backing up or in the same place, and that expansion. But that's what the idea is. So it gets bigger, but everything kind of remains the same. So this is what we do all the time, dilations, specifically, like if I was to take any image, let me get an image of a hexagon. Let's fill it in with black. Yeah, there, that works. So there's my hexagon. And if I were to take this hexagon and go like this, this is not a dilation. I'm changing it. It's not a dilation. But if I were to go like this, that is a dilation. And on my program that I'm using right now, only one of my corners will actually dilate it. If I pull this way, it doesn't actually stay dilated. Okay, so I have one corner that will maintain that, and that's this one that will do everything in the perfect movement. Okay, some programs that say basically any corner, just depends. So, but that's what dilation is to make it bigger or smaller, like the pupils in your eyes dilate. When you're excited, the black gets bigger or smaller, all the things with light and whatever. So that's what a dilation is, okay? And then when we're all done, we create similar figures. So as we continue, which polygon appears to be different, what makes it different from the others, and what do the other three polygons have in common, mark the corresponding parts of the similar figures. So we're talking about similarity. What sequence of transformations pass one onto the other? So we use the word similar to describe two polygons that look alike but may be different sizes. More specifically, similar polygons can be mapped onto each other with a sequence of rigid transformations and a dilation. For the sets of polygons below, 3 are similars, that is, they are related through a sequence of transformations, including a dilation, and 1 is not similar. So the other transformations will be shifting, translating, all those things happen too. Okay, and 1 is not similar. So when I'm looking at these, they all have 5 sides, so I can't use that. What do you think? So which figure is not similar? So the idea is that basically, if I took the smallest figure, which is A, I should be able to take A, times it by something to get B. Maybe it's 1.5, maybe it's 2, maybe it's 7. should be able to times it by something to get a new figure. And so I think D is the one that's not. See how D has this very, very, very rigid right angle right here? And if I take that angle and move it, that's not a right angle. That's not a right angle, and that is not a right angle. And that's what they mean by tracing paper. The angles should match when you've dilated. The angles are always, always, always the same. What's not the same is the size of the sides. So the angles always match, but the sides don't. So this one is wrong because I don't have a right angle. All right, so you're out. Okay. Which figure is not similar? That would be that one. The questions that we're answering are these. So I need these questions. So which a polygon appears to be different? What makes it different? It's D. And specifically, I'm going to go with the right angle clue to be in. You can pick something else. Like I don't think the side is the same slant. I mean, like the side, it looks funny. It's hard to describe, but the right angle was my clue. And you can pick a different clue because whatever your clue was is your clue. So then what do the other three figures have? My goodness. Love it when it gets stuck like that. Just a minute. Okay, so I think I've taken care of my technical difficulties. Sorry about the scribbling. I hope you actually didn't see it because it wasn't really there when I fixed everything. But anyway, what do the other three polygons have in common? Mark the corresponding parts in the similar figures. So what I'm going to do is I'm going to actually trace B and move it around. Okay, and so see how the angle is the same, and that angle is the same, and that angle is the same, that angle is the same, and that angle is the same. That's what they meant by use tracing paper to help you. So all the angles are the same, and it looks like the sides are about half. And B, not half, not double, but all the angles match. So with that to help me, B is a movable one, I would say this angle matches this angle, which matches that angle. So I'm going to use color to help me. This angle matches this angle. I'm going to fill these ones in. Matches this angle. Then these angles here are the same. Go ahead and do double rainbows here. In case you're colorblind, I don't want this to not be helpful. And then let's use purple. We're going to use 3 marks on this one. Starts to get hard. And then the last one I'm going to mark just with brown. And I'm going to mark it with a tip mark. So this one. Okay, so those angles all correspond. Now, correspond meaning that they're the same. That's the same kind of idea. But the other things that correspond here is the sides do. And that's kind of harder to tell. But we know that since A is the smallest figure, that we had to take A and times it by something to get the side length center B. So now what that something is, I have no idea. It looks like about 2, but I don't think it's purely 2. So like 1.9 or something. And then I took A again and times it by something to get C. So the sides also correspond, just something to keep in mind. What sequence of transformations? So I would have to take A, translate it to the right, translate it right, and then dilate it by a factor of something. And then A, translate it down and right, and dilate it by something. Okay, and what that is, I think this is probably supposed to be 2. and then maybe 3. So 1, 2, 3, like that, like whatever that number is, but that's the idea. What sequence of transformations? So we're translating. We can just use translate on all of them. None of them got flipped, but they can be flipped. We can translate and then dilate. Now, dilations are not rigid motions. They are not rigid motions. They do not maintain shape. These shapes are not congruent. They are not exactly the same. They are not congruent. It's very important that you understand this. So dilation, it does not maintain. It's not a rigid motion, which is why we did not talk about it in Math 1. Okay. So examine the triangles below. These triangles are drawn to scale. Are they similar? So we can take the smallest side here, 5, and times it by 2 to get 10. We can take the middle side, 8, and times it by 2 to get 16. We'd take the longest side, 9, and times it by 2 to get 18. I think yes, that they are similar because all sides got times by 2. Side lengths were multiplied by 2. I can also trace this shape and move it. Not like that. Move it, not the rest of it. Okay, hopefully I just have it. Yes, move it. Now, I'm going to have to flip it. So that comes right here. Transform, flip in y-axis. Okay, and then I'll have to angle it so that it fits in the angles. I'm going to turn it. I think that's probably good. And let's grab it and see how that's the same angle. And that's the same angle, and it's off because I drew it badly. But that's the same angle. So again, I'm going to really go, yeah, I got it. That's right. So this was O. I'm going to rewrite on my newly oriented triangle, which I'm going to stick on the inside, which will make it way easier to do that. This was O. This was G. And this was D. So C and D are in the same place. 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 Oh, what? All of them. Okay. And that D looks way like an O, so let me make it not look like an O. O and T are in the same place. So dog and cat, no, sorry, not dog and cat. That's too bad. O and T. So O and T. Nope, not that one. O and T are not in the same place. O and T are in the same place, and D and C are. So yeah, this one. It said more than one statement, so let's keep going. O and T are in the same place. C and T, yep, this one, these two. So sorry, not dog and cat, but dog and CTA, and Dago and cat, they are. So there you go. So that's our basic idea here. Okay. And that's, I think, it. That's it for similarity. So good luck. Hope you have a great time, and we'll talk about this when I see you again.